So in this video, we'll look at a couple more examples as relates to proof writing. So suppose you're asked to prove the following. Suppose you're asked to prove that the inequality 1 plus 2 to the n is always greater than or equal to 3 to the n for any integer n that's a positive integer. So sometimes you'll get to a situation where you're like, you know what, I totally believe it, and you go straight to your proof. And sometimes you get to a situation where you say, I totally don't believe it, and I can immediately see where it fails. And sometimes you get to this situation where you look at it and you're like, you know what, I have no idea. So in any of those cases, but especially the last one where you're not sure what's going on, a technique that you use is using test cases. Okay, this is where you get a feel for what's actually going on. Now, when I say test cases, this is where you'd plug in and look at specific examples of whether this, in our case, inequality is going to work or not. So the only thing here that's changing is the n. So the n can be any positive integer. It's supposed to work for all positive integers. So the smallest positive integer is n equals 1. So we can say here, hey, n equals 1. Well, what happens? Well, the 1 plus 2 to the n would be 1 plus, 2, which is 3. And the 3 to the n is really 3 raised to the first power, or 3. And for that case, we're fine. And we're fine there because the inequality includes the equal symbol at the bottom, that horizontal line down there. Now, if we continue out with our test cases, n equals 2, we'll look at 1 plus 2 to the n. Well, this is really going to be 1 plus 2 squared, or what is that, 1 plus 4, so 5. And then when we look at 3 to the n, that's really 3 squared, or 9. And here you check, all right, well, 9 is bigger than 5. Are we okay with 9 being bigger than 5? And the answer is no. Because what we get here is that we do not get the correct inequality. And as soon as you don't get the correct inequality, this guy, when n equals 2, is going to be a situation where that supposedly accurate formula doesn't work. Now, what happens if something doesn't work? It isn't true in all the cases it's claimed to be true. Well, that means that the entire statement isn't true. If you were originally building the statement, it would need to be adjusted or fixed. But if you're just evaluating whether this is a valid statement or not, what you would say is, no, this is not a valid statement. There's something wrong going on here. And in fact, for this one, what we'll see in the future is that inequality is actually going the wrong direction. It needs to be flipped, and then that would fix this statement. And in terms of writing this up, how you would explain this to somebody else, or how you would write the proof, or in this case really a counterexample, is you would say this statement is false, and it's false by way of a counterexample, specifically here when n equals 2, the inequality does not work. So this is our first example of dealing with a counterexample while we've been talking about formal mathematical proof writing. So let's get the specific details going on with counterexamples that you need to watch out for. So when you have a counterexample, the first thing is that you are given a statement. And that statement can be whatever it wants. That statement will typically look very, very similar to the times when you're actually proving when something is true. So sometimes these guys are really subtle. Now, specifically what you want to do with your counterexample, and this is, you can pull this from the naming convention too, is we're actually going to be looking for an example. So this means specific numbers that you're plugging in, where the given claim, that given statement, is false. Okay? So this is the one time when you're dealing with proofs where you're actually pulling out a specific example. Please note, in all other situations where you pull out specific examples, they are simply test cases, and if those test cases work, in other words, the symbols, the inequality, the equal sign, the whatever thing you're testing for, if that actually works, this gives you no information other than showing you, yep, good, okay, now infinitely more options to check. However, when you're dealing with a counterexample, because in order for a statement to be true, it has to be true in all of its cases, as soon as you found that one situation, that one example where the statement isn't true, that's disproved the entire statement. In other words, in terms of the truth table, the symbolic logic, we have shown that we don't have a tautology. And that's the reasons why counterexamples work just fine, but physically checking all of the examples that work is typically infeasible. Every so often your statement is so narrow that you've only got, like, say 100 things to check, and you could brute force it or use a computer to help you. But often you will have infinitely many things to check, and in that case it's not something that you can physically check all of those cases that you're hoping to be true. So let us get back to looking at a couple more examples, and these examples may be something that would be something that you would prove to be true, or it might be something that we would need to show is not true. If it's something that we're going to prove to be true, we're not actually going to do the proof here. We're just going to say, hey, yeah, this will be true. If it's something that we think is going to be disproven or not a true statement, we're going to go ahead and find the counterexample. All right. So suppose we have this next example, and this next example here is, suppose you have two integers a and b, where a divides b. Remember, a divides b means a is a factor of b. And then we want to show that a then has to be less than or equal to b. So pause the video right now. Go check out a couple of examples. See if you believe this or not. All right, at this point, you should have gone and grabbed a couple of examples, have a guess of whether you believe that this guy is true or not. Now, fair warning, I will go ahead and give you some information at the end. If you have positive integers for a and b, this is a true statement, but notice here, if you pick negative integers, and in this case I simply picked one negative integer, b being -4, here 2 is totally a factor of -4, but 2 is not smaller than -4, which means this is a counterexample. This is a situation where you do not have the thing you were hoping to have right there at the end. Okay? So that would be a counterexample. So what if we look at this next example, and I went ahead and have very little space here, so we'll just talk this one out a little bit. Again, if we think it's true, we won't prove it. If we think there's a counterexample, we'll try to look at it a little bit. So this one here says, show you've got two right triangles, that they have the same area if their hypotenuses have the same length. So in terms of what this is asking you, this says you've got two right triangles. So here's a right triangle. Here's a hypotenuse. Here's a second right triangle. There's the hypotenuse. So maybe this is hypotenuse A, maybe this is hypotenuse B. And the conclusion that we want to get to is that these guys have the same area. Now, with the two little sample triangles that I drew, this makes sense. But let's look at some more situations. Alright, so I've prepped up two little diagrams of two triangles, and let's see if this seems believable. So, when you're in doubt of whether it's believable or not, you always try to break it. Why? If you fail to break it, in other words, you get test cases that work, that just lends evidence that a proof is needed, that this may actually work in all times. But if you find a test case that fails, that immediately is your counterexample. So in this case, I'm going to be lazy, and I'm just going to pick on Pythagorean triple. So 3, 4, 5 for the lengths of our sides here. Now, our starting point in this particular statement says your two right triangles need to have their hypotenuses to have the same length. So that means here that we would have a 5 over for the length of that second hypotenuse. Now let's go ahead and check the area. Now for this first triangle, I'm going to go ahead and label the vertices. That way we can call it something. So if we look at the area of this guy, the area of triangle ABC is simply 1/2 base times height, which for a right triangle is you just multiply the lengths of the legs together, those two sides that are adjacent to the right angle, and divide by 2. So this should be an area of 6. So if this statement is true, the area of our second triangle should also be 6. And I'll go ahead and label the vertices here so we can call it something in just a second. Now let's try to break this. Okay, so I'm going to be pessimistic and say that this side DE right here, let's make it just to have a length of 1. Now, we can figure out what the third side of the triangle is going to be using the Pythagorean theorem. Pythagorean theorem states a squared plus b squared equals c squared. So we've got 1 squared plus unknown side squared equals 5 squared. Or the length of the unknown side squared equals 25 minus 1, or 24, which means if we take the square root of 24, that should be the length of our side EF. Well, the square root of 24 is not an integer, but that's okay, we can deal with that. So this tells us that this length of EF, our missing side, square root of 24. And let me go ahead and simplify that a little bit. We can pull out some of our square guys. Let's see, factors of 24 are 2's and 3's. We can pull out a 2, and that would be 2 root 6. Now, I don't recall what 2 root 6 is off the top of my head, but we could plug this into a calculator and figure out what the decimal length is. All right, now, at this point, we can totally find our area. So if we look at the area of our triangle DEF, it's 1/2 base times height. Now notice the 2 and the 1/2 are going to cancel. The 1 gets multiplied through, so we're simply going to get a square root 6. And while I didn't remember what the square root of 24 actually equaled in a decimal, I do know that the square root of 6 and the integer 6 are not equal to each other. So what we just found is a counterexample with these two right triangles as we just labeled their lengths. Those are two right triangles that have their hypotenuses exactly the same length, but we were able to find that by playing around with the lengths of their legs, we could actually get that the areas were not the same. So this would be an example of a counterexample that was not just number crunching that we were doing in the other ones, i.e. geometry versus algebra and number theory. Okay, so that's the crash course in dealing with counterexamples.